Wireless communication, but using the lights. It's very popular. It's called LiFi, and quite often it's using an LED as a communication channel. But an LED behaves very different from an antenna. So the communication system that uses the LED also has to adhere, has to take into account all these differences of the LED as a communication channel. And we are proud and very happy that our research into how these LEDs really behave is now published by IEEE in IEEE Communications magazine. A pretty popular story, but in this interview, in this story, in this discussion, we would also like to dive a little bit deeper into what we really see in the behavior of the LEDs. So with my team at Eindhoven University of Technology, we have been writing this paper.
I'm showing that I'm postdoctoral work with TU Eindhoven. I'm mainly work on the signal processing for optical wireless communication.
Hello, my name is Anton. I graduated the electrical engineering faculty of Eindhoven University of Technology. And my background before I graduated the electrical engineering was physics. And now I have the PhD title.
Hi, I am Shukufa. I'm still a PhD student, and my main background are signal processing and information theory.
So wireless communication over an LED channel, that is the title of the publication in IEEE Communications magazine. And of course, we look into a communication channel, a communication system in the way that it's usually been done. We feed data into a modulator, a driver that feeds the signal into the LED with its space charge region and its quantum well. You see a cross section of the LED on the right. Then the signals go through the optical channel and are being received. But we believe that not the optical propagation channel is determining, is limiting the performance so much, but it is rather the LED itself. And we've seen quite a number of models in the past describing the LED, focusing on certain aspects. What is new in this paper is that we really go back to the physics of the whole electron recombination. And by that, we more or less refute some of the early ideas, a model in 1972 that says that the LED is a clipping channel, because modern LEDs do not really hard clip the signal. Anton Alexey, you're an expert on the physics of LEDs.
Yes, that's true. If you use the modern LED, you can put significant currents through it and it will still emit light. And there are no physical phenomena that really can make the LED hard clip.
And that's very different from the early days that LED materials were very expensive and they were designed to give them the largest possible light output. Now they're operated in the place where they're most efficient and then still far away from the maximum output. So if we look in more detail into the LED, we see something different.
Yes, for sure. Modern LEDs, they have quantum wells, high efficient modern LEDs, they have quantum wells, and the carriers are injected in the quantum well and then they recombinate inside of it with different phenomena. But there are there is not only a problem of the quantum well, but also a problem of space charge region, because there are two of these things, and they can limit the modulation frequency, the 3 dB bandwidth of the LED.
And if I see this, it looks pretty linear all the way. Later on, we will go deeper into nonlinear effects, but if we look into it from a linear perspective, so we apply a DC bias and then put sinusoids, small sinusoids at different frequencies, this is what we see.
Yes, correct. So if we apply small signal modulation and measure of the LED, we can actually define the cutoff frequency corresponding to the quantum well and space charge region. And for illumination LEDs, the cutoff frequency corresponding to the quantum well is significantly lower than the cutoff frequency corresponding to the space charge region. That's why quantum well defines the 3 dB bandwidth of communication.
And that 3 dB bandwidth is pretty significant because it can already happen around megahertz or 10 megahertz. So really at frequencies which are hampering very high bandwidth communication. And in order to address that, we can apply special tricks. One of them is OFDM modulation, orthogonal frequency division multiplexing, where we really on every frequency do exactly what is the optimum to be done at that frequency. So on the left we see the LED channel, which is low pass, and now what can the transmitter do? It can put the same power on every frequency, or it could boost the higher frequencies, but that comes at a cost. And Shokofe Madani is the expert who looked into details of these strategies, of these algorithms. Shokofe.
As we see in the channel frequency of LED, we see that the lower frequency have better channel quality, and the higher frequency have a weaker channel quality. And the task of the transmitter in an OFDM strategy is to put a higher constellation and higher power at the lower frequency, and put lower power and lower constellation at higher frequency. So this is why people use OFDM.
And OFDM is very effective to do this, but OFDM is very sensitive to distortion. And that is becoming a problem if we use the LED and try to squeeze the maximum bitrate out.
Yes, apart from the linear model previously discussed in previous slides, we can also see the nonlinearity. Actually, the LED nonlinearity is the key challenge that for us to further increase the data rate in LiFi system. As we can see, in the eye diagram we measured, we can see the asymmetric closure for different levels, for example, for Pang signal. And also the red screw in this eye diagram we measured.
To understand these effects in a bit more detail, I think we have to dive closer into what is really happening in the quantum well. And this is the picture that we took from the IEEE Communications magazine, a pictorial explanation of what is happening, Anton.
Yes, so the main reason for the different rise and fall times is dependent of the recombination time on the carrier concentration. And why the recombination time is dependent on the carrier concentration inside the quantum well. Because we have three main recombination mechanisms. First one is Shockley-Reed-Hall recombination, second one is radiative, and third one is Auger recombination. And the first one is dependent on the concentration of the carrier, second one on the square of the concentration, and third one is proportional to the cube of the carrier concentration in the quantum well. That's why if you have different concentration of the carriers inside the quantum well, different ways of recombinations dominate at different levels of carriers.
Now, this is explained in terms of pictures, and IEEE Communications magazine does not allow us to have any equations in there, but in fact, this flow of carriers can be described as a differential equation. We are interested in a quantum well. So the change of the number of carriers inside the quantum well is the key thing that we are interested in. D and sub QW, that's the flow in and out of the quantum well, of course, is determined by the current, IN, but more interestingly, it's determined by the photonic effects. And as the picture just showed us, we have three of them.
Yes, correct. So the first one is Shockley-Reed-Hall recombination, and it happens through a trap between the conduction band and valence band. And it's proportional to the first power of the quantum well carrier concentration. Second one is radiative. Radiative recombination requires two particles. And during the radiative recombination, electron recombines with a hole and it emits photon. That's why it's proportional to the second order of the concentration.
And that's the one that we like for communication.
Yes,
But
because
the other ones we do not like.
Yeah, because it's the only recombination channel that actually contributes to light emission. And the third one is Auger recombination. It's very similar to radiative recombination, but the energy is released in form of kinetic energy of the third particle, third carrier. So therefore, there is no light emission during the Auger recombination, and therefore it's proportional to the cube of carrier concentration inside of the quantum well.
Now, in all the 4 years that you have been doing your PhD, that was the language that you have been speaking to us as a physicist. But the rest of the team is looking into it more as signal processing engineers. So we try to translate that into a signal processing model. And that could be done relatively easily. And it looks even like a linear filter, but it's a bit more than that linear filter. So we basically see on the lower right part that there is a low pass structure because there's a time delay TS and then a feedback A1, and that's basically an integrator, a kind of lossy integrator where A1 is slightly less than unity. But then that is a low pass effect that is still not radiating. It's this squaring effect that then feeds into A sub 2, which is really the light emitting part. So this squaring part is something that we see also affecting the carrier concentration, NQW. And this is again the part in A5 that in the end takes care of the emissions of the photons. So if this structure looks like a normal filter, it could be seen as a simplified Volterra filter, but then with squarings and cube operations. That is a reasonably good model for the LED, and that's something that we published in 2019 at the SPIE Opto Conference in San Francisco. And it looks like if we feed a pump signal into it, what we get out of it really resembles very well what we measure with the real LEDs. So this relatively simple model gives a reasonable model of what the LED does. And if the signal processing people look into this, they say, hey, I can invert this. Shokufe, you've been looking into the inversion of these LEDs.
Of this structure is much simpler than ultra series based equalizer, which are generic. Actually, those equalizer in literature has a lot of number of coefficient to be calculated from the training sequence, but this simple structure even allow us to think about finding the of equalizer blindly. So this is the topic that we have been working on.
And you really need only a few constants, a few parameters of the LED. And I even believe that these can be translated to really physics models, as Anton has been looking into it. But basically, we estimate them just as properties of the system without really relating them to junction heights and thicknesses of the materials. If we go a little bit further, then OFDM systems typically do not have a nonlinear equalizer. Basically, they just have an FFT, fast Fourier transform, to detect the signals on all the frequency components. And then any distortion basically results in distortion artifacts on different frequencies. The previous model also allows us to model how much distortion there is on each and every frequency. And that can be modeled in this way, where we basically massage a little bit the structure of the nonlinear model. We see that the distortion artifacts are created at the quantum well. So the distortion occurs based on the signal as it is present in terms of whole electron combinations and not of the current that goes in. So particularly the higher frequency components are attenuated because of the capacitance of the junction and create less distortion than the lower frequencies. Then once that distortion is created, we see that the signal goes in two ways. It goes directly to the output because of that squaring term in the generation of the photons. And we see that it is in our filter structure goes back to the junction capacitance, and there it exhibits a low pass behavior. And that is added together with the direct path constant D. Anyhow, we see that distortion components also show a very pronounced low-pass spectrum, similar to the signal itself. And I think that is now something that we have explained in terms of a model of the LED. These and other stories are in the paper in IEEE Communications magazine called Wireless Communication over an LED Channel. And of course, we would like you to cite this paper. There are no equations in it. If you like to have a somewhat more analytical model, we have two other suggestions for you. One is the SPIE conference in San Francisco, modeling and compensating dynamic nonlinearities. And in order to explain how these ideas can be used in a nonlinear equalizer, a paper in 2018 in IEEE Transactions and Communications is interesting. And with that, I think we all thank you for listening to this podcast.
Thank you.